Hi, welcome to the next video. Let's finish section 5.6 and chapter 5. Okay, so last time we talked about the sine inverse function, and so we're going to start this discussion with talking about cosine inverse. Okay, so let's look at the graph of cosine x, but let's look at the graph after we restrict its domain from only 0 to pi. Right? Cosine x is defined on the entire real line, but y equals cosine x is not a one-to-one function as it starts out. But if we restrict the domain of cosine x from 0 to pi inclusive, now it is a one-to-one function. It passes the horizontal line test, and so it is a one-to-one function. Okay, and so this is now our cosine graph with a restricted domain to make it one-to-one. Now, if you take the graph of cosine x with that restricted domain, and so I'm going to refer to cosine x now. When I say cosine x, I mean cosine x with the restricted domain for this lesson. Okay, so now whenever I say cosine x, I mean cosine x with the restricted domain from 0 to pi. Okay, so now the inverse of cosine x is with the restricted domain. Let's draw the graph of it. I'll use this pen marker because I think it has more ink in it. So if you have from -1 to 1, and for this is 0 to pi, then the inverse graph will look something like this. Okay, and this is across the graph at pi, y-axis at pi over 2. So this is y equals cosine inverse of x, which is arc cosine x. So cosine inverse x equals y if and only if cosine y equals x. Okay, sorry. Okay, so then cosine inverse x equals y if and only if cosine y equals x. Okay, and 0 is less or equal to y, less or equal to pi, restricting the domain. Okay, here y is the input of cosine. Okay, so this is defining cosine inverse. That's the graph of cosine inverse, or cosine x. So the cancellation equations are cosine inverse of cosine x equals x, and cosine of cosine inverse x is equal to x. This is for 0 less equal to x less equal to pi, and this is for -1. This is now the input of cosine inverse, so this is -1 less equal to x less equal to pi. Okay, the input of cosine inverse is from -1 to 1, so that x you put into cosine inverse ranges from -1 to 1. The input for cosine here is from 0 to pi. Okay, so those are the cancellation equations, but for cosine x and cosine inverse. So now let's talk about the derivative of cosine inverse of x. Okay, so if y, I'm going to put a line here, and let's work underneath that line. Let y equal cosine inverse of x. Then cosine of y is equal to cosine of cosine inverse x, which is x. Now differentiate implicitly with respect to x. We get that the derivative of cosine y with respect to x is negative sine y times y prime, which is equal to derivative of x, which is 1. That implies that y prime is equal to -1 over sine y. It's 1 over negative sine y. I just put the negative in front. So y prime equals -1 over sine y. Okay, but what is sine? What is y? Y is cosine inverse of x. So this is equal to -1 over sine of cosine inverse of x. because y is cosine inverse of x. I substitute y there for cosine inverse of x. Okay, and now if you look at if you do this right triangle trick like we did in the other example, here's a right triangle, and I'll let theta be cosine inverse of x, and this is going to be theta is going to be the angle of this triangle. So theta is cosine inverse of x. That implies that cosine of theta is equal to x. Okay, so cosine is the ratio of the adjacent side to the hypotenuse. That's x over 1. That's cosine theta, it's x over 1. And then by the Pythagorean theorem, this is the square root of 1 minus x squared. If you solve for this side for the Pythagorean theorem, you'll get this is the square root of 1 minus x squared. And so x squared plus the square x squared plus the square root of 1 minus x squared squared is x squared plus 1 minus x squared, which is 1 squared, which is 1. Okay, so this side is the square root of 1 minus x squared. And so this is negative 1 over sine theta. Sine theta is the ratio of the opposite side over the hypotenuse. So sine of theta is the square root of 1 minus x squared over 1, or just the square root of 1 minus x squared. This is negative 1 over the square root of 1 minus x squared. And so what we showed is that if y is cosine inverse of x, y prime is equal to negative 1 over the square root of 1 minus x squared. Okay, and so now we found the derivative of cosine inverse of x. d dx of cosine inverse of x is equal to negative 1 over the square root of 1 minus x squared. Alright. So let me erase this just because it's a graph of cosine with restricted domain. And so I want to write this also on the board. So d dx of cosine inverse of x, we found over there, is equal to negative 1 over the square root of 1 minus x squared. That's another formula that you d dx of cosine inverse x is equal to negative 1 over the square root of 1 minus x squared. And this is for negative 1 less than x less than 1. Okay. So let me put that here. Negative 1 less than x less than 1. Okay, so this on this board I have things you need to know about cosine inverse after we restrict the domain of cosine x from 0 to pi. Good. Okay. Cosine inverse. So the next board we're going to talk about tan inverse. Okay, so the x and y axis, and so now you have this asymptote, you have this asymptote, and so you have negative pi over 2 and pi over 2, and you have 0 here. Okay, so this is the graph of y equals 10x. From negative pi over 2 less than x less than pi over 2. Okay, so I've restricted the domain of tan x to only that part of it, so it's a one-to-one function. Right? Okay, so it's a one-to-one function that passes the horizontal line test. So the graph of tan inverse looks like this. Okay, so this is y equals tan inverse of x. And so if you take that graph and reflect it about the line y equals x, you get this graph. Okay, and so this is the graph of y equals tan inverse of x, which is another name for it is arc tan x. Okay, And tan inverse of x is defined by the statement tan inverse x equals y. If and only if tan of y equals x. Tan inverse is the inverse function of tan. Okay, tan y equals x, and negative pi over 2 less than y less than pi over 2. So we also include the fact that we're restricting the domain of tan for inputs only strictly between negative pi over 2 and pi over 2. Okay, so facts about this graph. So facts about tan inverse. Okay, the limit as x approaches infinity of tan inverse of x, as the graph suggests, is pi over 2. The limit as x approaches negative infinity of tan inverse of x is negative pi over 2. And so now the domain of tan inverse is the set of real numbers. The range of tan inverse is, well, the range is y value strictly between negative pi over 2 and pi over 2. Okay, and so you get that. Okay, and so that's good. Okay, so that's the stuff you need to know about tan inverse. Okay, and so next we're going to do 2 examples involving tan inverse. So another example, simplify the expression cosine of tan inverse of x. Okay, so simplify the expression cosine of tan inverse of x. So solution. Okay, so oftentimes when you see something like a trig function of an inverse, you want to draw a triangle. So we're going to do that again. So let's draw a right triangle, specifically a right triangle, and let theta be this angle here. Okay, cosine of tan inverse of x is equal to cosine of theta, where let theta be tan inverse of x. Okay, so tan inverse x is equal to theta. That means tan of theta equals x. And x is x over 1. Right? And if you look at SOHCAHTOA, the last 3 letters tell you that the tangent function is the ratio of the opposite leg over the adjacent leg. And so tan of theta is the ratio of the opposite leg over the adjacent leg. So you see that this leg has length x and that leg has length 1. By the Pythagorean theorem, the length of this side is 1, square root of 1 plus x squared. Okay, so the hypotenuse is that. Now cosine theta is the ratio of the adjacent side over the hypotenuse by this part. The cosine is the ratio of the adjacent leg over the hypotenuse. Adjacent over hypotenuse. So you get 1 over the square root of 1 plus x squared. And so simplify the expression cosine of tan inverse of x. We simplify it as cosine of tan inverse x is equal to 1 over the square root of 1 plus x squared. Okay. And that's it. That's the solution to that problem. Good. Okay, so next example. So I'll give you a moment to study that. Make sure you know it's right side down. Okay. Good. Okay, so next example, evaluate the limit as x approaches 2 to the right of arc tan of 1 over x minus 2. Solution. Okay, the limit as x approaches 2 from the right of arc tan of 1 over x minus 2. To help you visualize it, I drew the picture to help me visualize it. Arctan, the graph of arctan of a variable, right? I'm going to call it u, because so it's a different letter than the one in the problem. Well, hopefully that doesn't make it confusing. This is the graph of arctan of u, where this is the u-axis and that's the y-axis. Okay, that's the graph of arctan of u, right? And that will tell you that the limit, it will remind you that the limit as the variable approaches infinity of arctan of that variable u is equal to, this asymptote is pi over 2, that's negative pi over 2. This is equal to pi over 2. And the limit as u approaches negative infinity of arctan of u is equal to negative pi over 2. Okay, so we see these two limits, and you remember how the graph of arctan looks. That will remind you what these two limits are. Okay, these horizontal asymptotes are y equals pi over 2 and y equals negative pi over 2. Okay, well, the limit is x approaches 2 from the right. So let u equal to 1 over x minus 2. Then we'll leave this blank. Then blank happens as x approaches 2 from the right. As x approaches 2 from the right, what that means is that here's x equals 2. And so we're looking at x values that are approaching 2 but to the right of 2, which means that it's numbers slightly larger than 2 that are approaching 2. So if you plug in numbers slightly larger than 2 that are approaching 2, x minus 2, right, is a number slightly larger than 2 minus 2. You get a positive number here. But that difference is approaching 0. But it's approaching 0 from the positive direction. So x minus 2 is approaching 0, but positively. And so 1 over 0, positive, is positive infinity. Then u is approaching positive infinity as x approaches 2 from the right. And so the limit is x approaches 2 to the right of arctan of 1 over x minus 2 is equal to the limit as u approaches infinity of arctan of u. And what's the limit as u approaches infinity of arctan of u? It's equal to pi over 2 from the picture and from that equation. So the final answer is that the limit is x approaches 2 to the right of arctan of 1 over x minus 2 is pi over 2. And the problem's solved. And solutions. Problem's done. Okay? Okay, and so we calculate that limit in that example. Good. So next, let's find the derivative of tan inverse of x. I'm going to leave the picture and the limits there, unless I need their space. Okay, so let y equal tan inverse x. Then that means that then tan y is equal to tan of tan inverse of x, which is x. Now differentiate implicitly with respect to x. That means that the derivative with respect to x of tan y is secant squared y times y prime, and d dx of x is 1. So secant squared y times y prime is equal to 1. That means y prime is equal to 1 over secant squared y. Well, what's y? Y is tan inverse of x. This is 1 over secant squared tan inverse x. So this is 1 over secant squared of tan inverse x. So now let's find secant squared of tan inverse x using a triangle again. Okay, because we have the trig function, or squared of an inverse trig function. So here's the angle theta, and let theta be tan inverse x. And so theta is going to equal tan inverse x. Okay, that means that tan theta equals x. But if you remember SOHCAHTOA, then that tells you that tangent function is the ratio of the opposite side over the adjacent side. X is x over 1. So tan of theta is the ratio of the opposite leg to the angle theta, which is x, over the adjacent leg, which is 1. And so now the hypotenuse is the square root of 1 plus x squared by the Pythagorean theorem. This squared plus this squared is equal to that squared. 1 squared plus x squared is equal to the square of the square root of 1 plus x squared. Okay, so now we have this is equal to 1 over secant squared of theta. That's equal. Secant squared theta is secant theta squared. Okay, well, secant theta, so actually I'm saying I don't need these limits. So we're going to erase these two limits here. Secant theta is 1 over cosine theta. Okay, it's a reciprocal of cosine. Okay, so secant theta is 1 over cosine theta. Cosine theta is the ratio of the adjacent side over the hypotenuse. This is 1 over the ratio of the adjacent side of theta over the hypotenuse. And so 1 over cosine theta is 1 over the square root of 1 plus x squared, which is the square root of 1 plus x squared. So secant theta is the square root of 1 plus x squared. And so secant squared theta is equal to the square root of 1 plus x squared, which is equal to 1 plus x squared. So secant squared theta is 1 plus x squared. And so in the denominator we have secant squared theta, then you just put 1 plus x squared there. So this is equal to 1 over 1 plus x squared. And so what we found is that y prime, if y is tan inverse of x, then y prime, the derivative of that function, is 1 over 1 plus x squared. Okay? And so we reach the conclusion, so I'm going to edit the graph here. Don't need that now. So our conclusion is that d dx of tan inverse of x, y prime, is equal to 1 over 1 plus x squared. And so this is a formula you should definitely know this formula. When you talk about derivatives of inverse trig functions, this is an important one to know. d dx of tan inverse x is equal to 1 over 1 plus x squared. Okay, and so we derive that right here. We prove that this equation is in fact true from here, and the proof ends right there. Okay, so that's a discussion on tan inverse x. Okay. Good. Let's keep going. Okay, so now we talked about sine inverse, cosine inverse, and tan inverse. And so there's three other inverse trig functions we could talk about. Y equals cosecant inverse x. Y equals secant inverse x. And y equals cotangent inverse x, right? Those are the inverses of the three other trig functions that we talked about, right? So we have y equals cosecant inverse x, y equals secant inverse x, and y equals cotan inverse x. Let's define y equals cosecant inverse x. This is for absolute value of x greater or equal to 1. This is if and only if cosecant y equals x and y belongs to 0, pi over 2. Look at what endpoints I include and which ones I don't. Union pi, 3 pi over 2. Okay? So I'm just restricting the domain of cosecant here to make it a one-to-one function. Okay, here, y equals secant inverse x. This is for absolute value of x greater or equal to 1. And this is if and only if secant y equals x and y belongs to 0, pi over 2 union pi, 3 pi over 2. Okay, y equals cotan inverse x. This is for any real number x, any x belonging to the real on the real line. If and only if cotangent y equals x and y belongs to the set 0, pi, not including 0 or pi. Right, so when I have the open intervals, they don't include the endpoints. When I have the bracket, it does include the endpoints. So it includes this one, and that one, and that one. That's what the brackets are, okay? Parenthesis, parenthesis, bracket, parenthesis, bracket, parenthesis, parenthesis, bracket, parenthesis, bracket. Okay? Okay, good. So we have the definitions of the three other inverse trig functions above that line. Okay, so next let's talk about, let's have a table of derivatives of inverse trig functions. So table of derivatives of inverse trig functions. d dx of sine inverse x is equal to 1 over the square root of 1 minus x squared. d dx of cosine inverse x is equal to negative 1 over the square root of 1 minus x squared, like I showed before. And d dx of tan inverse x is equal to 1 over 1 plus x squared. So we proved those three equations. Okay? Now the other three derivative functions. We have these three inverse functions, and there's derivatives of those three functions, and so I'm just going to state them here. We're not going to prove them. d dx of cosecant inverse x is equal to negative 1 over x times the square root of x squared minus 1. d dx of secant inverse x is equal to 1 over x times the square root of x squared minus 1, and d dx of cotangent inverse x is equal to negative 1 over 1 plus x squared. Okay, and so those are the table of the 6 derivative functions of inverse trig functions. So derivative of sine inverse x, derivative of cosine inverse x, derivative of tan inverse x, derivative of cosecant inverse x, derivative of secant inverse x, and derivative of cotangent inverse x. Okay, so these 6 equations are the 6 derivative equations for inverse functions. Okay, but even though there's 6 equations, there's simple memory things you could do to help you remember them. For instance, this is positive, that's negative. It's almost the exact same expression, right? The derivative of sine inverse is 1 over the square root of 1 minus x squared. The derivative of cosine inverse is negative 1 over the square root of 1 minus x squared. These are just negatives of each other, right? The negative sign is for cosine inverse, okay? Here, the derivative of tan inverse x is 1 over 1 plus x squared. The derivative of cotangent inverse of x is negative 1 over 1 plus x squared. And so this is just the negative of that, right? And see, the negative is for cotangent inverse. Here, for derivative of secant inverse x, it's 1 over x times the square root of x squared minus 1. Well, the derivative cosecant inverse x is just the negative of that. It's negative 1 over the x times square x over minus 1. Just the negative of it. So 6 equations are really 3 equations. Okay? And the negative signs are for the inverse trig functions that start with c. Cosine inverse starts with a c, there's a negative sign. Cosecant inverse starts with a c, negative sign. Cotangent inverse starts with a c, negative sign. And so the 3 inverse trig functions that start with a c, cosine inverse, cosecant inverse, and cotangent inverse, those are the 3 with negative signs. And the 3 without starting with a c, sine inverse is positive, tan inverse positive, secant inverse positive, all right? So there's 6 equations, but the derivative of inverse functions that start with a c are negative, and the derivative of inverse functions that don't start with a c are positive. And so with that simple fact, remember that, and 6 equations become 3 equations, okay? And you just remember that sine inverse and cosine inverse are negatives of each other. Tan inverse and cotangent inverse are negatives of each other. And secant inverse and cosecant inverse are negatives of each other. Okay? Right, because cotangent is the reciprocal of tan, right? And so in that way, you can see how these could be the negatives of each other. These two are like the inverses, like cosecant inverse. These are like the reciprocal functions. So cosecant inverse and secant inverse are negatives of each other. Sine inverse and cosine inverse are negatives of each other. Okay, so you can kind of visualize in your mind, you know, how you break these 6 into pairs, and in those pairs, they're negatives of each other. Okay, so then you only have 3 to remember. Okay, and so this might be the easiest one to remember. Derivative d dx of tan inverse x is 1 over 1 plus x squared. And so this is most common to come up when you need the derivative of an inverse function. I think it's just because it's the easiest to write down and remember. It's not because of any, this is 1 over 1 plus x squared, right? But all 6 of them, you just remember a slightly more complicated expression, okay? So the 2 that are most common are the first one, d dx of sine inverse x, which is 1 over the square root of 1 minus x squared, and d dx of tan inverse x, which is 1 over 1 plus x squared. Those 2 are the most common. Okay? If you remember those 2, you really remember 4, right? If you remember those other things. And then there's just those 2. This would be the hardest to remember. Okay, so those are the 6 derivatives of inverse trig functions. Okay, let's keep going. Example. Differentiate f of x is equal to x tan inverse of the square root of x. Okay, solution. So let's use the product rule. So f of x is the product of the function x and tan inverse of the square root of x. So f prime of x using the product rule. Remember the product rule, I'm just going to write down here. The product rule says that f times g, the derivative of f times g is f times g prime plus g times f prime. Okay. And so, if you thought of this as one function, this is the other function, then f prime of x is equal to x times d dx of tan inverse of the square root of x plus tan inverse of the square root of x times the derivative of x. Okay, so all we need to do is find d dx of tan inverse of x and d dx of x and plug them in. This is 1, right? So let's find d dx of tan inverse of x. Well, first remember that d dx, from the derivative of inverse tan function, d dx of tan inverse of x is equal to 1 over 1 plus x squared. You just remember that. Now d dx, applying the chain rule to that, we already used the product rule, so I'm going to erase this. So this is our derivative function from the last word. That implies that in combination with the chain rule, that d dx of tan inverse of a function f of x is equal to 1 over 1 plus f of x squared times f prime of x. And so you should know this formula also, okay? d dx of tan inverse of f of x is equal to 1 over 1 plus f of x squared times f prime of x. And once you know that, this problem becomes much simpler. Then this is equal to x times, what's d dx of tan inverse of, d dx of tan inverse of the square root of x is 1 over 1 plus the square root of x squared times the derivative of that function times the derivative of the square root of x. Okay, that's plus d dx of this is this, plus tan inverse of the square root of x times the derivative of x, which is 1. Okay, now we simplified the problem even further to just find the derivative of the square root of x. Okay. Okay, well the square root of x is x to the 1/2. So d dx of the square root of x is d dx of x to the 1/2. That's in root form, that's in exponential form, so we can demonstrate the same thing. dx of x to the 1/2 is 1/2 x to the negative 1/2. Right? You put this in front, and then 1 times 1/2 is 1, and then you subtract 1 from the exponent. 1/2 minus 1 is negative 1/2. So d dx of the square root of x is 1/2 x to negative 1/2. Okay? So we got that formula here, so you need to know this formula. And then just plug in for dx of the square root of x, you get 1/2 x to negative 1/2. So this is x times 1 over 1 plus the square root of x squared is x. So x times 1 over 1 plus x times the derivative of the square root of x, which I said was 1/2 x to the negative 1/2 plus tan inverse of the square root of x times 1, which is that. And that's the answer, f prime of x. That's what it is. There you go. Okay, so the example is differentiate f of x equals x times tan inverse of the square root of x. The answer is f prime of x is equal to x times 1 over 1 plus x times 1/2 x to negative 1/2 plus tan inverse of the square root of x. That's the final answer. Okay, and so that's good. Okay, that's good. Okay, so the two most useful integration formulas are the integral of 1 over the square root of 1 minus x squared dx is equal to sine inverse of x plus c. That's one. And the second most important one is the integral of 1 over 1 plus x squared dx is equal to tan inverse x plus c. Okay, so these are the two most useful integration formulas. So these are the two most important integration formulas. Okay, so know these two. Know them. Okay, they're from the fact. These are from the fact that d dx of sine inverse x is equal to 1 over the square root of 1 minus x squared, and d dx of tan inverse x is equal to 1 over 1 plus x squared. Okay? So because the derivative of this is that, the most general antiderivative of this is this plus c. And because the derivative of tan inverse of x is that, the most general antiderivative of that is this plus c. I'll say it again. Because the derivative of this is that integrand function, because the derivative of this is that. The most general antiderivative of this is that plus c. Because the derivative of this is that. The most general antiderivative of that is this plus c. Okay, it's going in the opposite direction. Okay, and so these two are the most important integration formulas to know involving inverse trig functions from the 6. Okay, those two. So make sure you know these two. Okay, make sure you know those two. So I'll give you a moment to write them down. Write maybe something here down if you need to. Good. Check the camera. Good. Okay. Let's keep going. Next example. Find the definite integral from 0 to 1/4 of 1 over the square root of 1 minus 4x squared dx. Okay. So to do that, we're going to use U substitution. Okay. And so let's also, as a fact, let's remember that the integral of 1 over the square root of 1 minus x squared dx is equal to sine inverse x plus c. Okay, so we're going to need this equation for this problem. The integral of 1 over the square root of 1 minus x squared dx is equal to sine inverse x plus c. Okay, so we need to get this integrand to look more like this. We have 1 over the square root of 1 minus x squared here. We have the square root of 1 minus 4x squared there. This is 1 minus something squared. So we want 1 minus something squared here. And so we can do that easily. I'll show you. So if you take the integral definite from 0 to 1/4 of 1 over the square root of 1 minus 4x squared, and this is equal to definite from 0 to 1/4 of 1 over the square root of 1 minus 2x in parentheses squared dx. 4x squared is 2x in parentheses squared. You square 2x, you get 2 squared times x squared. That's 4x squared. Now we have it of the form. Now we have this of the form 1 over the square root of 1 minus something squared. But that something is not x, it's 2x. And so we're going to use U substitution. Let u equal 2x. Then du equals 2 dx. It's also called the substitution rule. By the substitution rule for definite integrals, we get, so actually before I do that, let me point this out. If I was to use the substitution rule for definite integrals, u would be replacing the 2x here. But I need to replace the dx, and so I need a 2. So what I'm missing is a 2. So I'm going to fix that by putting a 2 there, because I need one there to substitute 2 dx for du. And so what I'm going to do is I'm going to add what I need in the expression there. I'm going to put a 2 there. But what I did was I now multiplied it by 2, and so to fix that, I'm going to multiply the outside by 1/2. And so I fixed the problem I caused by putting a 2 there. And by multiplying by 1/2 also. So I multiplied 2 to 1/2, and now it's fine. So now here, again, I let u equal 2x, then du equals 2 dx. So du is 2 dx, u is 2x, and so now I can substitute everything with x in it for u's. By the substitution rule for definite integrals, we get the above meaning this, equals 1/2 definite integral, I'll do the limits later, 1 over the square root of 1 minus 2x, which is u squared. And then 2 dx, which is du. So now we have that. And now substitute everything with x in it in terms of u. And now the new limits of integration are when x is 0, u is 0. And when x is 1/4, u is 1/2. Okay? So now we have that definite integral. Okay? And so we have this improper integral here. This tells you that the definite integral from a to b of 1 over the square root of 1 minus x squared dx is equal to sine inverse x evaluated from a to b by the fundamental theorem of calculus, because this is an antiderivative of the integrating function. Now the variable is just u instead. So this is going to equal 1/2 times sine inverse of u evaluated from the lower limit to the upper limit, from 0 to 1/2. Okay? This is equal to 1/2 times sine inverse of 1/2 minus, I'm going to erase this and this here. I used it. This is sine inverse of 1/2 minus sine inverse of 0. Sine inverse of 0 is 0. Alright, so sine inverse of 0 equals 0 because sine of 0 is 0. Sine of 0 is 0, so sine inverse of 0 is 0. Sine inverse of 1/2 is equal to pi over 6 again, because sine of pi over 6 radians is 1/2. So sine maps pi over 6 to 1/2. So sine inverse maps 1/2 to pi over 6. So sine inverse of 1/2 is pi over 6, and sine inverse of 0 is 0. So we have this equation, and now we have this one. Those are the values. So that's equal to 1/2 times sine inverse of 1/2, which is pi over 6, minus sine inverse of 0, which is 0. And so we have 1/2 times pi over 6 minus 0. That's 1/2 times pi over 6, that's pi over 12. That's the final answer. The final answer is pi over 12. And so the definite integral of 0 to 1/4 of 1 over the square root of 1 minus 4x squared dx is equal to pi over 12. And now we're done with this example. Okay, and so now that example is, again, done. So I'll leave this a moment so you can look at it. Okay, keep going. So example, evaluate the integral of 1 over x squared plus a squared dx. Okay, so this example is evaluate the integral of 1 over x squared plus a squared dx in solution. Okay, well, remember from before, the integral of 1 over 1 plus x squared dx is equal to tan inverse x plus c. Okay, and so here we have the integral of 1 over 1 plus something squared. This is the integral of a squared plus x squared. The integral of 1 over a squared plus x squared, just reverse the order. And so if we could make that a squared a 1, then it would start fitting nicely with this formula. It would start looking more like this one. And so let's do that. Let's try and find a way to do that. We have the integral of 1 over x squared plus a squared dx. So now I'm just going to switch the x squared and a squared. This integral of 1 over a squared plus x squared dx. I want that to be a 1 where there's an a. So in order to make this a 1, I would have to divide by a squared in the denominator. And so we can do that. So we're going to divide the numerator and denominator by a squared. Well, if I just divide the denominator by a squared, it's the same as multiplying by a squared. So I'm going to put it this way. This is equal to 1 over a squared times the integral of 1 over a squared times a squared plus x squared dx. What I did was I multiplied the numerator by 1 over a squared and the denominator by 1 over a squared. You know what, let me put it this way. Basically, I'm just going to put, that'll make it easier to see what I did. Okay, so here's the numerator, that's the denominator. I multiplied the numerator and denominator by 1 over a squared. And so it's still equal. Now I'm going to take this 1 over a squared and I'll move it in front. So this is 1 over a squared times the integral of 1 over. Now if I multiply this times this, 1 over a squared times a squared is 1 plus x squared over a squared dx. Well, x squared over a squared is x over a squared. So because I want something squared here. This is 1 over a squared, integral of 1 over 1 plus x over a in parentheses squared dx. Now it's starting to look more like that, right? This integrand now looks more like that integrand. But instead of an x squared, it's an x over a squared. And so I'm going to use u substitution. So I'm going to let u be x over a, because that's what's weird. Let u equal x over a. Then du equals the derivative, which is 1 over a dx. By the substitution rule. This is not a definite rule, it's an indefinite rule, so it's just called the substitution rule. By the substitution rule, we get the above, which is this, equals 1 over a squared, the integral of, so when we substitute x over a for u, that's fine. But now we need dx, we need a 1 over a. So we're missing a 1 over a. So to fix that, first I'm going to put, what I need is a 1 over a here. So I'm going to put that 1 over a there. And then when I put a 1 over a there, this is 1 over a squared. There's 1 over a squared there. When I put a 1 over a here, though, I need to fix it by multiplying the outside by a. So I'm putting the a there. So multiplying by 1 over a here, I'm fixing it by multiplying the outside by a. And so by the substitution rule, we get the above equals, well, a over a squared is 1 over a. And this is the integral of 1 over 1 plus u squared. And then 1 over a dx is du. And so that's du. Let's now get that. Okay. So now this matches perfectly with this formula. Now instead of x, it's just u. And so now the result is that integral is tan inverse of u plus a constant. So this is 1 over a tan inverse of u plus the constant, skipping the step where we need the algebra. We'll get a second. Okay, so then so we use this. We just use that for this equal sign. And now that's equal to 1 over a tan inverse. Now u is x over a. And so instead of u, you substitute back x over a because the original problem was in terms of x. And so u is x over a, so tan inverse of x over a plus c. And so what did we find? We found the integral of 1 over x squared plus a squared dx is equal to 1 over a tan inverse of x over a plus c. Okay, and so we evaluated the integral of 1 over x squared plus a squared. It's 1 over a tan inverse of x over a plus c. And now we're done with that example also. Okay, good. Okay, so that is the end of chapter 5, the end of 5.6, and the end of chapter 5. Okay, so do the homework, and next lesson we'll be doing chapter 7. Okay, so thanks for tuning in. See you next time.